In research NLP these days, there's always a lot of talk of probabilistic models and machine learning, but if you actually look at large systems under the hood, what you'll almost always find is that they also make quite a bit of use of regular expressions in various places. And for many tasks, it turns out that regular expressions are just a very practical and capable way of specifying various kinds of natural language patterns. I'm going to show you one example of this now by showing you how we use regular expressions for the English tokenizer inside the Stanford NLP tools such as the parser and part of SpeechTagger, or for the core NLP suite overall. Okay, here we are with the code for the Stanford English Tokenizer. So what it is it's a large deterministic regular expression. And so what it's written in is with a tool called JFlex. So JFlex belongs to a family of what are commonly called in computer science lexers, which is just another word for tokenizers, which take a sequence of characters and cut pieces one token at a time off the front of it. So there was the original Lex that was part of Unix, and then Flex, and then this is JFlex, which is a Java compatible version. Let's scroll down to where some of the regular expressions are used to define character classes. Often what you find is that many of the regular expressions aren't actually very complicated, that they're really nothing more than lists that have been put into regular expressions by putting vertical bars in between for ordination. And so, for example, we see that in several places here. So here we have one for abbreviated months, and here we have one for abbreviated days of the week, and that continues on for some of these other ones like American states and various other kinds of person name title acronyms down here. But let's go on a little bit further to one that's a bit more interesting than that. Okay, so here's one for phone numbers. This is the kind of ill-documented regular expression that's a little bit hard to actually get your head around, but are much used in practice. So at the very top level of this regular expression, things are divided up by this alternation right here. And on the right-hand side of the alternation, there's a pattern where the separator is being used as dots. And so that one's separated out as consistent use of dots, because otherwise it's easy for the regular expression to go wrong and also recognize various kinds of decimal numbers and other patterns. And so that part of it is actually the easier part. So we can have at the beginning, optionally, the use of plus signs, which are used in Europe and most of the rest of the world as an international prefix for country codes. And then we can have the country code here, which is just numbers of the range 2 to 4. And then all of that is optional. And then after that, we've got a first set of numbers, which can be the area code, the dot, then the second set of numbers, which I guess historically was the exchange, and then finally the third set of numbers. And so these sets of numbers are then being given a length, so this has to be between 3 and 4 numbers, this has to be 3 and 5 numbers, and the area code has to be 2 and 4 numbers. And so those ranges are chosen so that they'll work with the phone numbers of a bunch of the countries around the world. But if you know well your international phone numbers, you'll realize there are actually some cases that won't still be recognized by those. So what then if we go to the left-hand side of the regular expression? It's effectively doing the same thing, but is more complex. So that the first part of it is again going to recognize things like optional country codes. So you can see the same piece over here for the optional country code, but it's allowing in some other possibilities. So here we've escaped the parentheses, so you can actually sort of have some numbers that are put inside overt parentheses. And further on, we've got this character class where we're allowing a variety of other separators apart from period. So we can have a dash, which again needs to be escaped. There can just be a space, or there can be a non-breaking space. So here's a Unicode escape for a non-breaking space. And so then overall this will allow it to recognize a bunch of formats for phone numbers. So it'll recognize almost all American phone numbers and generally does pretty well with things like UK and Australian phone numbers. If you want an example of where it doesn't work, the normal phone number format in France is you just have pairs of digits with spaces in between them. And that's not included here. And the difficulty isn't sort of writing a regular expression that matches that. It's in this context of a deterministic regular expression matcher of managing to write one which won't also wrongly match various other things, such as numbers that are just appearing as a sequence of numbers for some other reason. Well, I hope that's given you some idea of the use of regular expressions in NLP systems. If you poke around in other NLP systems, I'm sure you'll find lots of other examples. Commonly when people want to match particular patterns, whether they be patterns at the level of words or patterns at the level of parts of speech, they can just be very convenient and practical methods to solve many practical tasks.